Hey everyone, welcome back to my daily coding series. Today is day 77. So today I'm going to look at a dynamic programming question. So I was just kind of scrolling through some one-dimensional dynamic programming questions and clicked on perfect squares. So I haven't looked at this yet. So let's get started here. So we're given an integer and we have to return the least number of perfect square numbers that sum to n. Okay, a perfect square is an integer that is a square of an integer. So you've seen these before: 1, 4, 9, and 16. Okay, so first I want to say that any number, I'm thinking any number can be written as the sum of perfect squares because you can do all ones, like in the worst case. Like, I don't know, if you have this kind of reminds me of, so if you have like 3 or something, you could just represent it as 3 ones. So this kind of reminds me of coin change. And if you don't know what that problem is, you're given denominations of coins, and then you have to figure out like a target amount. What's the minimum number of coins that you can make the number in using the denominations? So it's kind of the same exact thing, except now our denominations are perfect squares. So typically, so if we have 12, for instance, a greedy approach of this would just be like, okay, let's pick the highest perfect square that is less than or equal to 12, and that would be 9. And then we would say, okay, now we have we have 3 left. So what's the highest perfect square that is less than 3? So 1, 1, and 1. So we just repeat that process until we get 12. So this would be the greedy approach. As you can see, there's actually a faster way to do it if we do 4 fours. So we can't just do the greedy approach. We'd have to use some sort of dynamic programming element to know which is the fastest, or I should say the least number of perfect squares. And if we look at the second example, we have 13. So this one you do 9 and then 4. So in this case, the greedy solution would actually work because you pick the largest square that is less than or equal to 13, which is 9, and then the remainder would be 4, and then the largest square that is less than or equal to 4 is 4. So in this case, the greedy works. In this case, it does not. Our only constraint is that, so 1 has to be a positive non-zero number, basically. Okay, so my thoughts of looking at this is, so 12 we know first of all that we can reach all. So if we have, we can reach all perfect squares less than 12 in one perfect square only. So we know that these all are 1. So I think what we could do is kind of do a bottom-up solution. So we'll start with a 1, and we say that, okay, we can reach 1 in 1 coin. 2, if 2 is a coin, so when I say coins, I'm just talking about this because I'm pretty much just trying to remember how to solve coin change, because I'm pretty sure it's like exactly the same. So then we'd say 2 is the minimum. Well, we'd look through every coin. So because this is not yeah, so if we have like our perfect squares that are less than 12, so I'll assume that we have that. I can make that. So it would be like 1, 4, and 9. So for every coin, we could do, so we'd see 4 and 9 are higher than it. So we'll look at 1 and we'll say, okay, we need one more 1 coin from this. So we'd see that if we add this value to the coin, this would become 2. 1 plus 1 is 2. So this would tell us that to get the value 2, it would be 1 plus whatever this value is. So it's a little confusing because it's all ones. So if we look at 3, so 1 is, so we'd subtract 3 from 1, 3 from 4, and 3 from 9 and see if any of those are in our memory. So 3 minus 1 is in our memory. So then we're going to do 3's value is 2 plus 1, which is 3. Okay, 4. We're going to subtract 4 from 9. That's negative. 4 from 4, which would be 0. So 0 is in our memory. So we'd say that's, okay, so 4 then equals 0 plus 1, which is 1. And then we can keep doing this, right, until we get to our target number 12. This is my idea. So then when we get to 12, we'll subtract each coin from it and say, okay, is 3 in here? So let's, yeah, so I guess I'll fill these out quickly. So 7, 8, 9, 10, 11, and 12. Okay. So we'll say is, let's see. So 5, we'll say, if we subtract 1, we see that 4 is in here. So that means this would be 2. If we subtract 4, that would give us 1. So we could either do 1 plus 1 here, or we could do this 1 plus 1. I guess I would just start from it would be the minimum of all of those, actually, is the correct answer. So you'd do all of them and then put the minimum. Okay, so 6. So 6 minus 9 is negative. 6 minus 4 is 2. So we'd look here and we'd say, okay, it's between 3, or 6 minus 1 is 5, so 3. 7, that's negative. 7 minus 4 is 3. 7 minus 4 is 3, so we'll look here and say, okay, it's between 4, or 7 minus 1 is 6, so it's between 4 and 4, which will just be 4. So 8, same thing. We'll look at, actually not same thing. So 8 minus 4 is 4. So it's between 2. So we can do this plus 1, or we could do 8 minus 7, and then the value, 8 minus 1, and the key is 7, so the value of that plus 1. So it's between 2 and 5, so 2 is the minimum. So 9 minus 9 is 0, so that's the minimum. 9 minus 4 would be, so that'd be 3. So those are the different ways that you can make it. 10 would be 2. 11 would be, so if we do this, minus 9 would get us 2, so it would be between 3 or 4, which would give us, so if we subtract 4, then that would give us 7, so between 3, 5, and 3, so we'll just say 3. And now 12, if we subtract 9 from 12, that would give us between 4, if we subtract 4, that would give us 3, and if we subtract 1, that would give us 4. So the minimum of those is 3. So this would be our final answer. So that's like the bottom-up sort of way to do it. Okay. So I'm going to call it squares. So this will be like 149, for instance. So it's going to be, whoops. It's going to be all the squares up until n. So we'll say 4, and then this will just be n. So I guess I could call it 4I in n, or for num. Well, no. Okay, we'll say I equals 0. Or we could say in range n. Yeah, that works. Okay. And then we'll also say like our memory or memoization, or I'll call it DP, I guess, which will be a dictionary. Or I guess we could just have an array of length n. So we'll just start it all at zeros. Okay. Right, so n would be 12, so we'd want it to have 0. So 12 zeros, but that would only give us 11 indexes, so we should do +1. So this will give us 0 and n as an index, and everything between. Okay, so now what we're going to do is each number, we're going to calculate the minimum value and add it to DP. So I'm going to assume that this is built already. So we'll say like 4 square in squares. Okay, so now we're going to do so one, I don't know what I'll call it yet, but basically we're looking at the number value minus the square. So that would give us, for instance, this, and then we want to look at the value at that index. Right, so we want to look at the value at that index plus 1. So this would be like the next. So for instance, when we look at 12, we're looking at 12 minus 1 gives us 11. So this is 11. So we're looking at DP of 11, which gets us this. Then we're going to access that, right? And then plus 1 would give us 4. So yeah, right. So we could say like, I don't know exactly what to call that yet, but then the idea is if it's smaller than something that we've already found, then we'll update it. So we only want to keep the minimum of all of those. Yeah, and then we'll say that DP, so like once we're done and we found the smallest one, we will say that DP of num equals the minimum one that we found. Yeah, and then at the end we're going to return DP of n, which would be this one. So now we need to generate the squares array. So how would I do, so how can we generate all perfect squares? So it defines, it is the product of some integer with itself. So we can say maybe like I times I for I in range. I don't know, I'll just say 100. Or maybe, can you? Maybe I can use a while loop here and say while I times I is less than n, squares dot append I times I, and then I would go up by 1. So I don't know if you can use a while loop in list comprehension. I'm not really sure. Could you say maybe something like I times I while No way, right? No, yeah, I don't know. I'm not sure if you can do that or not. So, okay, so I equals 0, and then we're going to check while I squared is less than n, we'll append it. And then I guess we could start I at 1 because we don't really want 0 in there. So, okay, so I'm going to print squares and then exit out of the function just to see if this is giving me the intended values. Okay, so here we have an error that I can't append. Okay, yeah, I forgot parentheses. Okay, so let's, that's still not going to work. Okay, there we go. Let's see if this works. Okay, 149 and then 149 as well. So that seems to be working. So now what I'm going to do is see if this works or if I have an error somewhere in the code. Okay, so here we output 0 and 3. So let me print what all of DP equals and see if the behavior looks good. So this, whoops. So this does look weird, I think. This is the first test case, right? Yeah, this is not what I was expecting. So let me see. Okay, so first of all, it's not running for the last one, so I think we would say n plus 1. This would still give me the wrong answer, I'm pretty sure. So it just happens to work for this one, but the array is completely incorrect. Hey everyone, I'm back. Sorry about that. Okay, so where was I? Yeah, I think DP, so this array wasn't working properly. It was, yeah. So let me, at every step, it's the minimum of temp. So it becomes infinity. So I'll print temp before and after every step. And then I'll also print num here. Like that. Okay, so it's getting set. Oh, maybe if it's negative, is that why? Oh, that's probably why. So it's negative. Okay, so I'll say okay. So what is this, I guess? Like new min? Or like possible number of squares? So it's equal to dp of num minus square plus 1. So if num minus square is greater than 0. I think that was the issue. So this should fix that. So it was going into a negative index, which was causing problems. So am I still printing DP? Yes. So what happened? They're all infinity now. It's impossible for them to all be negative. So if, let's say num is 1, or I guess num would start at 0, which we don't really want. because 0 should already be decided for us. Okay, so 0. Okay, so 1. So it should print out 1. Num equals 1. And then for square and squares, num minus square. So it would be 1 minus 1. I think if it's greater than or equal to 0. So in that case, it would be 0. So we'd set it to, yeah, and I think the whole engine should be fixed by that. Yeah, okay. So the 1 was never getting set as 1. So that's what was happening there. Now I don't know if this will work for everything else. Okay, so we do have an incorrect test case. It does sort of appear to me to be like an edge case though. Okay. And temple, this will always be true for at least 1. So we'll never get infinity if everything works correctly. So in this case, n is 1. So how many? So there should be 1. So why is that not happening? So we're going from, so 1 is being infinity. Let me use this as a test case and try it again. So let me see. So n is 1 and we're outputting null. We're outputting null. So let me print what dp looks like. So dp looks like 0 and infinity. And we're returning infinity. Okay. So for 1, we'll start at 1 and n plus 1 would be 2. So we would execute at least once with we would execute at least once with 1. So in that case, it would say 4 square and squares. Oh, so what? So maybe this has to be equal as well. Yeah, that I think that's the problem, is because there are no squares. Yeah. So we need to make sure that we include, if the answer is a perfect square, we need to make sure we include that in squares. Okay, and there we go. So let's clean it up a bit and think about this may also be, can we just go until the square roots perhaps? All right, I'm back again. Sorry about that. So I was thinking we may be able to optimize this part by using list comprehension and say maybe something like I times I for I in range, like the square root of n. But that may be tricky if n is not a perfect square. So I think I'll just keep it like that. Now this temp part, I don't really like this variable name. Num is okay. This is okay. DP is okay. So temp. So what does this represent? This is the, I deleted all my comments, but it's the minimum. It's a possible coin amount, or I guess I could call it like num squares. Yeah, I could call it num squares. So I don't think we have temp. Yeah, so it's like the number of squares that we need to get to this number. And I start it at infinity because I always want the first one to be equal to this. Instead of infinity, I mean, like I said, it will always be overwritten. Yeah, so I think that's fine. Yeah, but if I said, let's say like 10 to the 5, that should also work. because sometimes I know infinity like costs a lot of memory. So in this case, so it's greater than the upper bound of, is it of n? Yeah. We may be able to put this something lower even, like if we're constrained on memory, because just the way that the problem would work. Because if we're this big anyway, we know that there is definitely a combination that's less than this, for sure. So we don't even really need the number to be this big. So maybe using math, we can reduce it, but I don't think it's really an integral part of the algorithm. So yeah, that's num squares. I feel good about that one. I was able to kind of pattern match it to a problem that I've done before. And luckily I remembered, or kind of was able to walk through again the logic of coin change, the bottom up solution at least. Yeah, great problem. Yeah, that was a lot of fun. So thank you guys for watching. I'll be back for day 78.